Hello, I'm Ben Foley. Today I'll be talking about automatic speech recognition for everyone. First, I'd like to acknowledge that I'm presenting from Gubbi Gubbi lands and that I acknowledge the traditional owners, past, present and emerging, of the country from which I'm presenting. So I'm the Transcription Acceleration Project Manager. This project is an initiative of the ARC Centre of Excellence for the Dynamics of Language and the University of Queensland. The Centre of Excellence, or CODAL, is a group of universities researching the impact that technology can have on language, transforming the science of language. So I'll talk more about the Transcription Acceleration Project when we come to it soon. So today, automatic speech recognition. At first, a bit of context. The world has many languages. This image shows the density of languages across the globe. The colours don't represent language families, they're just showing the groupings of languages on different continents. But we can see that there's an incredible density of languages on our planet. Different estimates. The Ethnologue estimates about 7,000 languages in the world. Glottolog estimates about 8,500 languages. So this includes what some people might call dialects, or we could also call these language varieties. The diversity is spread unevenly across the globe. So there are 60% of languages in 17 of the countries, a small proportion of the population and a tiny proportion of land area. The diversity of the languages is also not reflective of the similarities between neighbouring languages. So you might have a language with, say, a very simple phonetic inventory, or the sound systems in the language, might sit next to a language that has a very complex inventory. This rather strange map shows the diversity by distorting the countries where the most diverse languages are. So we can see that Papua New Guinea, just to the north of Australia, here is enlarged. Papua New Guinea is an incredibly diverse language ecosystem. There are up to 800 languages in small areas. Even the top of Australia here is covered by this dark blue patch, or this dark blue band, which indicates that there's a great diversity of languages in the top slice of Australia. Across the middle and the eastern sides of Australia, we have a lot of languages as well, but they don't have the same diversity as some of those in Papua New Guinea. This map of Australia shows some of the language names, either spoken or recently spoken. It's worth having a look at gambay.com.au, and you can also watch videos of people speaking about their experience with language. So the people on the left-hand side here feature in videos on this map. So there are over 800 languages documented on this map. And here we see some groupings by colour, which do show some similarities among neighbouring languages. So language is important for encoding knowledge. It's significant for people's sense of identity. Who are they? And it's becoming even more realised now that language is significant for people's well-being. If people don't speak or use their language, then it's more likely that they are less well, their sense of well-being is lower. There's a lovely example here of the relationship between language and cultural knowledge, ecological knowledge, from Guniwinku language in Arnhem Land, where the fish and the tree that are co-located have the same name, Bokhorn. If you find this tree in the bush, you know that in the water below it, in the pool, you'll find its fish. So the name encodes the relationship between these entities. The significance of language to identity is important when we're talking about language technologies, because we can't study and use language in isolation from the people. It's important to recognize that people and their communities must be involved in the development of technologies. Again, we'll come to that later. Something else that's worth considering is that people don't need to be fluent in a language to identify with it, and for that language to shape their sense of identity. So we have 7,000 or 8,500 languages estimates in the world. This diagram is a representation of the availability of technologies for these languages. So this comes to us courtesy of Google's Dan Venice. He's a speech scientist, a linguist, machine learning expert at Google in the speech team. And he's been working with us on some of the language technologies at UQ. So Dan put this language pyramid together as a way to show how some of the languages in the world have access to some of the technologies, but not all. So 7,000 living languages in the world, about half of those, or half to a third of those, have some sort of written tradition. For a lot of these languages, this written tradition is very recent, possibly in the last few hundred years, some even in the last 100 years. Almost all of these writing systems are supported by Unicode, which is a text encoding standard. And almost all of these Unicode scripts can be represented by Google's Noto fonts. So those of you who have used digital input over the years, say mobile phones, typing in different languages, may have come across the typing and then seeing a representation of what you've typed on a different screen, where the character you've written is represented by a blank rectangle instead of the character that you thought. This blank rectangle is known as tofu in the industry, and so this Noto font that Google has released is an attempt to represent every character in Unicode so that you can confidently type on one device and see it represented as you expected on another. Significantly, smartphone keyboards are today available in over 900 language varieties and covering 95% of the world's population in their first language. It is said that smartphone keyboards are one of the most significant language technologies, as it gives people the mechanisms to write in their own language, communicate and participate in the digital spaces in their own languages, rather than falling back to English or Chinese, or one of the kind of dominant languages. When we get to speech to text or speech recognition and text to speech, we're right down to these technologies only being available for 130 languages for speech recognition tech, or 60 languages for text to speech. So we've gone from 7,000 living languages in the world down to speech recognition systems only being available for about 130, and this is through Google. So there are a few other providers, but there's very little diversity in that. Google are one of the Google have maybe the most coverage, and then Microsoft and others have some support for fewer languages. So there's a great gap there in the availability of this technology for the world's languages. So in the research that I've been working in and the development of technologies, we're trying to fill that gap. This is a lovely list that was put together by Richard Little, Indigenous Language Technologies in Canada, where the availability and complexity of languages has been used, complexity of language technologies has been used to sort of rank the ease of which and the availability of which language technologies are out there for the world's languages. So the simpler technologies, so by simple, we think maybe they're simpler to set up, they may be simpler to run, are more widely available for many languages. So keyboard layouts, so smart keyboards, fuzzy search, these sort of systems maybe require less data and are typically simpler to install. As we move down this list, we come into technologies that are more complex to run, maybe require more specific data sets, and maybe even greater amounts of data. At the bottom of this list, speech recognition and machine translation. So these are language technologies which are very complex to set up and require large amounts of data to use. So there's the correlation here between these being difficult for communities to set up for themselves. So to this point, people have been reliant on providers like Google to build their own speech recognition systems. So why some languages and not others? Availability of skills in the community to set up speech recognition of their own. And why does Google support some languages and not others? Well, that often comes down to this economic basis. Google's interested in ad revenue, and if you don't have a large speaker population or an easily accessible data source to train a speech recognition system, then it's unlikely that they're going to build speech recognition support for your language. Speech recognition requires hundreds or more typically thousands of hours of transcribed recordings to train the systems. And we'll talk about one of the challenges of that in a moment. So what are my motivations for working in speech recognition? Having access to speech recognition technology is a critical thing for languages in the world today, where so much interaction, social interaction, business interaction is done through these devices. And more it's done through a speech interface. So in the last few years, Google report a 400% increase in voice traffic using the Google Maps system, which is extraordinary to think of. Hindi, Google Hindi is the speech recognition system which is putting through the most data. So it's a great increase in the use of these technologies for these languages that are not English. So the participation in these is significant. Crossing the digital divide, they say if a language has a representation in the digital space, these days it's more likely that this language will continue and will thrive. Without the support, the technology support, then more languages will sleep or fall out of regular use. Language documentation is the activity of recording a language. So we think of those 7,000 languages in the world. They are not all documented, many of them are, but the efforts to document these languages are ongoing. And one of the main activities that language documentation includes is the recording of a language and then writing a text equivalent of that speech so that people can kind of analyze it later, or maybe make interactive games or make learning resources using both of those, the speech and the text forms. This slide shows some activities by codal researchers and community members. So we've got some people working in the Pacific here, we've got some people working in South Australia, some in Central Australia. Each of these groups is recording their languages in different ways and using different technologies. But there's a bit of digital in all of those. For all of these situations, the speech recordings will be then taken away and transcribed. So what is transcribing? It's the writing the text form of some speech. And it's notoriously slow. We held a survey a few years ago where the average response of those people who participated in the survey was that it takes 39 minutes to transcribe 1 minute of speech. And for some of the respondents, it was up to 250. So the time it takes to transcribe depends on the complexity of the language, the fluency of the speaker, and other factors, including the noise of the recordings. However you slice it, it takes a long time to do this. And when people are documenting dozens or hundreds of hours of language recordings, then the task of transcribing all of that becomes impossible. It's just not achievable in a single person's lifetime of transcription. So the obvious question is, can speech recognition help? Well, yes, but speech recognition requires data to train, and we're getting caught in a catch-22 situation of not having enough data to train a system to help us transcribe the untranscribed data. Some experiments were done in the last few years with a technology called Kaldi, which is an open source speech recognition toolkit. It's been around for about 15 years or 10 years or so. It's quite a mature piece of software. It's industry level, it's industrial grade, wins all of the speech recognition competitions. So in the last few years, people have been experimenting with using Kaldi to develop speech recognition systems for their own languages. These three in particular, so Alexei Michal and Oliver Adams, have been working on some phonemic transcriptions of Yongling Na, Chitino, and Maori. Sorry, they were not using Kaldi, they were using a system that they built themselves called Persephone. Robbie Jimmerson working on a North American First Nations language called Seneca, and Zara Maxwell Smith working on Indonesian English corpus, all reporting that although the systems don't provide the type of quality of results that Google's systems do, nonetheless they are useful. So Jimerson's experiments showed that by using speech recognition on small quantities of data, they could still improve their transcription speed and quality by fourfold and double. So it made a big impact to them to have speech recognition as a first pass, or the speech recognition system providing a hypothesis for which they would then edit. This is also reported by Alexei with the NAR dataset, that it used the Persephone tool to provide a first pass transcription, which he would then edit. And for him, it made a significant difference in that it put him in a frame of mind of being an editor rather than a writer, and it makes that process a lot easier. The results that we see on the screen here are from Zara's experiments, where the top row is the transcription that she's written, and the bottom row is something that has been generated by the Kaldi system. And we can see that it's picked up some of the words, and it has missed quite a few, but it's found, or it's recognized some of the parts of the words. So even though the whole words are not identified, some of the parts of the words are recognized, and even this is useful. So this experiment was done with just 1 hour of transcribed recordings. So it's a very small training set, but it's getting some useful results that can make the task, her task of transcribing more of that recording session, a lot easier. Here are some more results. This is from a language in Central Australia, which shows some really extraordinary really extraordinary results from a tiny amount of training data. So the top row again here is the human transcription. The middle row is something that has been generated by the speech recognition system. And the third row is also from the speech recognition system, but some additional text corpus has been added to build up its knowledge of the words. So this system has been trained on only 10 minutes of training data, 10 minutes of language data. So this means that the recording that the system was trained with was only 10 minutes long. It's a small set. It's learnt the words in that corpus or that collection of recordings quite well. It wouldn't necessarily then adapt well to a conversation, but it has picked up those words really well. These are some more experiments with a language, a Nafsan language. This is languages from Vanuatu. Again, the top number 1 experiment is very good. The second experiment is very poor. So the first experiment was done with 2.85 hours of recordings. So this means that the user had just under 3 hours of recordings that had been faithfully transcribed, and fed these into the system, trained the system on these, then got these test results back, where again the top row is the human transcription. This is what the person did themselves, and the bottom row is what the machine, the speech recognition system, hypothesized. So this experiment shows some really good results, again with quite small training data. The bottom experiment is poor, and the reason for this is that in that small data set, the 2 hours, there were multiple languages and multiple speakers. So the machine, the machine learning system, didn't get to learn well enough. There was not enough data provided in the experiments for it to identify the sounds in the system. So at this level of work, the systems tend to perform better when they're a single speaker, when we're training with just one person's voice. And if you can provide multiple occurrences of a sound of a word, then it's likely that the system will perform better. This process of training a system, getting some results, and then editing them, we refer to as semi-automatic speech recognition. So automatic speech recognition is the sort of thing where you've got a production quality system with very low error rates. So Google type systems which have an error rate of in single-digit percentages, which means it might get one word out of 100 wrong. The systems that we've been working with for more of the world's languages might get more like every second word wrong, but it still seems to be useful. To an automatic speech recognition system with high quality or low error rates, you would expect to speak into and obtain the transcription and then be able to use that, say, directly into a translation interface or directly into some kind of voice assistant to book your holiday or to schedule a calendar invitation or some such. With these semi-automatic speech recognition systems, we expect that after we've obtained a transcription from the system, we're likely to need to edit it. But still, the process of doing that editing is expected to be a bit more beneficial than starting from scratch. Now, the challenges of this semi-automatic speech recognition is that technology is complex, and still the data is not so readily available. When we first started playing with Kaldi, our first workshop a few years ago, we had 20 or more software engineers, and over 2.5 days we installed it. So it took us 2.5 days to install the tool. It was quite an excruciating process. So this Dan Venice, in the center of the photograph here, came to us from Google and advised us to start playing with Kaldi, and we did eventually get the system working, and in the last half day of those 3-day workshop, we obtained some transcriptions for a language called Obui from the Indonesian islands. It's an Austronesian language in an eastern Indonesian island. It was quite a painful process, but we saw that the results would be useful for more of the people working with the world's languages, more language workers, linguists. It was quite clear that it was going to be beneficial for people. This is a typical screen of Kaldi, and I guess for some of you, you would be comfortable looking at this all day long as it flashes by rapidly. But for linguists and language workers, to be confronted with this is very opaque and quite terrifying for some of the users. When the interface gives you a feedback that this is probably a bad idea, is not very confidence building. So our response to this challenge of the technical complexity was to develop Elpis. It's a user-friendly interface for speech recognition. And today I'll talk about the process by which we designed and built Elpis and where it's at the moment. So you can see that to go from this type of interface, which though it's a computer scientist or a software engineer might be comfortable with it, for somebody who's not grown up with the command line or the terminal, this would be very confronting. For someone who's more used to a windowed environment, a graphical user interface, this type of screen would be much more encouraging for people to use. Elpis is a technology stack, pardon the jargon, where we wrap the fundamental speech recognition tools of Kaldi and now ESPNet in layers of tech. So we have a graphical user interface which is built in React, which is served by a Python Flask server. All of that is bundled up in a Docker container, and we call all of that Elpis. The original version didn't have the React graphical user interface. It was a series of Python scripts, which we still have access to the command line to use these tools, but for most of the users, the graphical user interface is the way that people are interacting with the speech recognition tech. On the right-hand side here, you can see the stages in the speech recognition process, where we have some sort of input, being some language recordings, some audio, and some transcription. So ELAN is the name of the software that many linguists use to transcribe their audio. So we accept audio files and these ELAN transcription files. We resample the audio, we extract the transcriptions from the ELAN files, we convert them to a standard format, and then we build a word list and a pronunciation dictionary out of them. Now these are fed into, these are the requirements for running the Kaldi speech recognition model. So once the data has been prepared, training happens, and with the model we can input some untranscribed audio and obtain an inferred transcription. So the URL at the bottom of the screen is where the code lives, github.com/codal, Center of Excellence for the Dynamics of Language, /Elpis. So how did we go about designing it? It was an 8-week summer scholars program a few years back, and to the horror of the engineers on the team, the first 4 weeks were spent getting to know the users and the workflows that people use to work with their languages. We participated in the summer school held in Canberra. This was a linguistics summer school, so we sat through seminars on topology, language topologies, variationism. You might recognize a couple of the people in the front of the image there. And then following these discussions at the summer school, we sat with a few individual linguists and observed their behaviours, their ways of working in excruciating detail. It was quite a diverse user group. We met what we'd call a field. We'd met field linguists. We met linguists who work in labs. We met phonologists. So a field linguist is somebody who goes to a community and does recording, does documentation. Phonologists study the science of the sounds of the language. So across the gamut of linguistic types, we met representatives and we got to know the ways that people work. We looked at mapping these methods of working into similarities and then lining these similarities up with those stages of data preparation, training, transcribing that the existing software used. So we didn't want to reinvent speech recognition technology from scratch. Knowing that Kaldi itself was very powerful, we were satisfied with developing an interface for it. Once we'd worked out that alignment, we ran a card sorting activity. So this is a process by which we idealized, or we came up with what we thought was, based on the conversations, what we thought would be a reasonable workflow for people, that would cover all of the individual differences. And then we separated those from each other. So we took out the sequential relationship, and we asked the users to realign them or to arrange them in the way that made most sense to them. And for the most part, there was a very strong correlation between what we thought the nominal sequence of events would be and what the users reported. But you can see that there were some points here where the cards are coloured red or yellow, where there was a difference of opinion. So in these situations, the user may have expected this card, say a red card, to occur somewhere else. So where it's red or yellow, then we have a mismatch of the sequences. And some of them were not too far out. It was quite an interesting process to go through. Then we went to wireframing, which was sketching out the steps, the stages in the process. And this was done to then pass back to the users to see if it still made sense, and to work out which widgets, which components the developers would need to start mocking up an interactive. So this was done as a static. These are images, these are not interactives. But it was a way to start thinking about how are the pages built, what are the components required. We went to a mid-fidelity prototype, so this was a clickable interface. It didn't do any actual speech recognition training, but it accepted data and it stepped through the stages. So again, this gave us a point by which we could check back with the users to see if we were still on track. Much of what is now in production is derived from this mid-fidelity prototype. This is an example of how the user testing occurred, where we printed out the screens that people were looking at and people could write notes alongside as they went through the process. So people were following a user testing protocols guide, which gave some information about what the tool was doing, and people could note where there was still confusion or where people needed more reinforcement about what was going on. Since then, we've been doing a lot of code quality cleanup. So the tool was sort of released, and then we scaled back on developing to clean up code, because when you're prototyping, it doesn't always make for high quality code. So there's still the legacy of some of those early code development in there, but slowly we're going through and diligently removing single letter variables. As anybody who's worked with Nic before knows, that's high on the priorities of cleaning up things, adding types. And for a while we had reasonable test coverage. Nic Buckeridge did his honours thesis last year on building some transformer importer factories to make dealing with different forms of data import easier. So the idea here is that while linguists, for the most part, use the Elan software, other linguists use another program called Prat, and yet other linguists or language workers particularly might use Excel or plain text files as their means of transcribing, or the way that they're documenting the language. So we need to have some facility to accept all of these diverse input formats. So the transformers are a way of abstracting the importing of the language data. Current work is we've just released a second engine in Elpis. So it was for the last while it has been solely a Kaldi orthographic transcription system. So orthographic meaning word based, so the system recognizes words. It can tell which is the most likely word to come after a suggested word. Kaldi uses these hidden Markov models and Gaussian Mixture models. It's a very basic recipe. It's one of the oldest, sort of 10-year-old recipes. It's not a neural network, but it was selected because these HMM GMMs still work very well when you've got low quantities of language data to train upon. So typically, if you have 100 hours of training data or language data to train on, then you're more likely to get better results from a neural network. But at less than 100 hours of language data to train, your performance will probably be better with the Gaussian mixture models and less computationally intensive. So it's more likely that people will be able to run these systems on their own laptops, which is significant for situations where there might be ethical considerations or privacy or rights and permissions restrictions around uploading language recordings to, say, a cloud server such as Google or Amazon. So some of the languages in Australia, the language communities don't accept that the languages recordings would go to cloud servers. They insist that the language recordings stay local, they stay in the community. So even for some situations, processing a set of language recordings at a university might not be considered okay by those communities. So one of the design constraints of building Elpis was that it could run on a laptop in a community. So just recently we've released another engine, or we've added another engine to Elpis. Again, this is with the significant input of Nic. Without Nic's insights and continual refactoring of Elpis, we wouldn't be able to have these features. So this second engine is a phonemic transcription, which is a transcription that doesn't recognize words, but it recognizes the sounds in the words, the sounds of the language. So the phonemes, the phones, these words just mean the sounds of the language. And this uses this ESPNet, which is a brand new speech recognition system. And specifically, it uses a bidirectional long short-term memory recurrent neural network with projection as its engine. For more information about that, get in touch and I can send you a paper. The ESP network has developed off the back of the Persephone language tech that I mentioned earlier. So Oliver Adams, when he was doing his PhD in Melbourne a few years ago, he built this speech recognition tool called Persephone, which did phonemic transcription extraordinarily well with only 35 minutes of data. Again, the more the data you have, the better it would perform, but he was getting quite good results. Low error rates in the single-digit error rates, I think it was, for very, very small quantities of data. He's since moved over to supporting, or he's rebuilt that recipe in ESPNet using ESPNet. ESPNet is a kind of PyTorch architecture that looks like it's achieving similar error rates. So these two new engines in Elpis, we're currently in the process of user testing how these two engines sit together, but the technology, the back end has been built. Now we're working on user testing the front end, the interface. And this is what it looks like at the moment. So these screenshots are hot off the press. These show the training process for both of the systems, both of the engines, so Kaldi in the background and ESPNet in the foreground. The Kaldi recipe is being sliced up thanks to MacLeod into separate stages that you can also read the log files that Kaldi gives out. So the log files are hidden by default. This is significant, again, for the general user, that stuff is just meaningless and at worst scary for people and can be a real turn off. But for the more advanced users or for support people working with language workers, then the logs can be interpreted to find out where things went wrong. So this is a mechanism where the logs are hidden in these accordion interface things, and you can click the little arrow there to show the log, potentially copy it and paste it into support Slack channel or email it to a friendly developer. So these two systems are coming on quite well. Future work, we're looking at mechanisms to save and load models so that people can share the speech recognition systems that they're building. And we are investigating bundling models with the software so that users can adapt them. So potentially ship Elpis with an Australian, maybe an Australian English speech recognition system, or a Central Australian Arandic language speech recognition system, or maybe a Western Desert language system. So this would lower the barrier even further for people if we could bundle a reasonably good quality system with the tool. Then potentially users would not even need to train their own systems. If they could use something that's similar, then that could reduce the barrier of entry even more. And we're interested in decoupling the transcription into a smaller interface as well. So currently the training and the transcription happens in the same interface, which means that the code is quite bloated, and there's potential for the transcription to happen in a much lighter interface. And as always, there's plenty of bugs fixes to do. So if you are interested, jump onto the URL there and come and help out. We accept pull requests. We love pull requests. And that, I think, is all from me. So there were a couple of questions in the chat. Marav, was I able to respond to that? The question was about what do I mean by 1 hour of training? Models trained on 1 hour of language data. So this means that we provide 1 hour's recording. So somebody, a person might speak the language for 1 hour, and that 1 hour recording gets transcribed faithfully. Then that's used to train the model.
All right. Well, I think that is all the questions. I just want to say a big thanks to Ben for giving us talk about Elpis and how all that stuff works. It's really appreciate your time. I know you're quite busy. In terms of next week, next Tuesday for UQCS, we have our annual general meeting where we'll be deciding on the 2021 executive team as well as some other general society business that we need to perform. We're holding this as an in-person event in the Hawken building in room C207 on Tuesday from 6 p.m. For all the information about our AGM, check out our Facebook page for all the info, as well as if you would like to nominate yourself for the 2021 committee, that is all there as well. But other than that, thank you so much for tuning in, guys, and we'll see you next time.